these same sets. And the question I want you to answer is, what are the limit points? I'm going to abbreviate limit points. What are the limit points? What are the interior points? What is the what are the other definitions we have? Isolated points. Now, notice that I'm asking you first to do it for R, and then think about the discrete metric. Okay. So take a couple of minutes. We'll take a couple-minute break, and you can stretch, and we'll try to answer these questions. Oh, before the break, let me see what your questions are. Yes, Dylan. From here on out, it's not a standard enough notation to do that. So if you do use it, you should remind the reader that's a discrete metric. Question? Yeah. Oh, excellent question. Is point B an interior point according to the definition? No, why not? Excellent, because B is in N, but B is not in E. B is in the neighborhood. So this is, in fact, a good example to put out here. B is not an interior point of big B. Excellent question. Okay, we'll take a couple-minute break, and during the break you can think about these examples here. No, next year, next spring. It's taught at the colleges every spring, and it alternates between Pomona and Harvey Mudd. I want to keep that. I want to keep that. How's it going? All right. Did Richard ever make it here? Richard Trong.
What are you going to do in your combinatorics research project? Because there's not a description up on them.
There isn't. Yeah. I haven't. Problem is, I haven't decided.
Oh, okay.
Yeah.
Like,
are you applying for RUs?
Yeah. And
okay.
So I was just sort of curious, like, because that sounds a little bit interesting, except like I want sort of.
Yes, more details. Yeah. So I guess the first thing I have to decide is whether I'm taking students this summer, and I'm not sure about that.
Oh,
Yeah.
okay.
Yeah, that's the main obstacle. But if there were a project, it would probably have something to do with triangulations of polytopes. Polyhedra.
Oh, okay.
Yeah, bounded polyhedra called polytopes. Higher dimensional polytopes. Either that or some project involving convexity. Yeah, but I may not be taking students.
Okay, because the application
tomorrow. Oh, right, yes. Yeah. Let me try to figure that out this week. Yeah. Okay, are we, I guess let's resume. So let's think about these examples. There are 6 examples here. The empty set. That is a subset of the real line, isn't it? Does the empty set have any limit points? No. Well, let's see why not. Willie says no. Why not, Willie? Okay, so you're saying it has no limit points because to be a limit point, so you're claiming that no point of R is a limit point of the empty set. So maybe it's easier to use the negation here. Is it true for any point P, there is a neighborhood of P in the real line that completely misses the empty set? Yes, trivially. Okay. The other way to see it is, of course, to go back to the original definition and say, is it true that every neighborhood of P, whatever the P is, contains a point of the empty set that's different from P? No, because there's no points in the empty set. Okay, happy with that? So, empty set has no limit points in the usual metric. What about under the discrete metric? It still is the case that any point P has a neighborhood around it that completely misses the empty set, correct? Good. So the empty set has no limit points in either situation. What about the entire real line? Does it have limit points? Yes, every point is limit point. Very good. What about in the discrete metric? Under the discrete metric, remember the discrete metric is balls could be single points or the whole thing. Is it true? So are there limit points? If the subset is the entire real line, are there limit points? Can P be a limit? Let's draw a picture here. Here's R, and I'm looking at it as a subset of itself. And I want to know, does it have any limit points? And some of you claimed what? It has no limit points? You want to justify that? Give me a point P. Is it true that P is not a limit point? Well, to not be a limit point means there is a neighborhood that completely misses other points. Is there a neighborhood of P that completely misses other points under the discrete metric? Yes, because under the discrete metric, the balls are points and the whole thing. Okay, so notice that in our discrete, P has a neighborhood, namely just P, that completely misses, that does not contain other points of E, which is R in this case. So E, which we're letting be R, has no limit points in R, discrete. That's the claim we just made. Okay, everybody happy with that? Let's just think about it. We're not going to do all these examples, but let's think about another example. Does R as a subset of itself have any interior points if the metric is discrete? Yes? Now I see at least one person shaking their head no and one shaking their head yes. So let's have a debate here.